In some cases, we only want to concentrate on partial symmetries and total symmetry. And the reason for that is that in most cases, we know how to handle these. So the first thing that we do is, if we want to do just partial symmetries and total symmetry, of course, what we will do is we will generate the Boolean orbits for each partial symmetry. Now that's a reasonably complex process. The first thing we want to do is we want to determine what the symmetry type is, the conjugacy class of the symmetry. So in figure 15, we show how the various partitions of an integer correspond to various types of partial symmetry. In the column on the far left in figure 15, we have 4, 1. That means we have a partial symmetry in 4 variables and 1 independent variable that isn't symmetric with any other variable. On the second line, we have 3, a partial symmetry in 3 variables and another partial symmetry in 2 variables, and so on as I go down through this list. Now, generating these partials or these partitions of an integer is actually a fairly straightforward process, and there are a number of different descriptions of the algorithm out there. Donald Knuth, in his latest book, has described this algorithm and how to, how to organize the algorithm and how to generate these partitions of integers. Although I think the algorithm is a little obvious. What we do is we start with 4, 5, for example. We'll start with an array of 5 elements. The first element will have 5 in it. The next 4 elements of the array will contain zeros. And I go through the array in reverse order, looking for a non-zero element. When I find a non-zero element, I subtract 1 from it and add 1, and place a 1 in the empty spot. In the case of 4, 1, subtracting 1 from 1 gives us 0, so we want to go on to the next element. We subtract 1 from that, and giving us 3, and we take the entire rest of the 5 number and put that into the next array element. So then we'd have 3, 2. As I'm going through it again, I find this 2, and that would give me, I would split that in 2, giving me 3, 1, 1. Again, working from the end, I have 3, 1, 1. I ignore the 1s. When I get to the 3, I subtract 1 from that, put that in the next element, and then put whatever is left in the third element. And that's basically the procedure that I use for generating all of these different partitions. These are called partitions of an integer. It's a descending sequence of numbers, or non-ascending, perhaps is a better way of putting it. And non-increasing, I guess, is the way you would describe that. And when you have this list of numbers, it has to add up to whatever number it is you're partitioning. So in the first column there, all of the sequences of numbers add up to 5. Middle column, they all add up to 6. And the right-hand column, they all add up to 7. So that's the first step. Now, let's suppose, I'm going to the next line after figure 15 here. Let's suppose that we have a partition such as 4, 3, 2, 1. Well, in order to figure out all of the different partial symmetries that this sequence of integers describes, the first thing we do is we have 10 inputs, so we take 10 things 4 at a time to fill in the group of 4. Once we've done that, we take 6 things 3 at a time to fill in the group of 3, and then 3 things 2 at a time to fill in the group of 2, and then the last element is just whatever's left over. And this will generate all of my partial symmetries as long as the integers are all distinct. If I have 2 integers the same, as I do in some of the examples up above, for example, right here I have 3, 3, where I have 2 identical integers. Here 2, 2, 2, 1, and so on. If I have 2 integers greater than 1 and they are not, and they are the same, I have to be very careful with that, because if I select all combinations of, say for this one, 2, 2, 1, if I select all combinations of 5 things taken 2 at a time and then 3 things taken 2 at a time, I'm going to end up creating duplicates. And the reason for that is, if I have 1, 2 for the first pair and 3, 4 for the second pair, that's the same as having 3, 4 for the first pair and 1, 2 for the second. And so I have to be careful not to handle the identical numbers identically. I have to be careful to handle them correctly, is what I'm trying to say. So what I will do in the case of having a sequence of identical numbers, when I generate the partition, I will make sure, or the combinations, I will make sure that everything is specified in ascending order. Okay, so if I have 1, 2, 3, 4, I would never generate 3, 4, 1, 2. I would always make sure that the pair with the lowest number in it comes first, and so forth. Once I've done that, I've got all my partial symmetries. I have several algorithms here. The first is generating a partition of a number. The next is generating a sequence of combinations. I'm not going to go through those algorithms. They're sort of standard algorithms. And so and eventually I'll end up generating all partitions or all partial symmetries. Okay, the number of partial symmetries given a certain number of inputs is given in figure 18. You will notice, if you compare it to the previous table that listed all of the subgroups up to S sub 18, that these numbers are considerably smaller. Even though they're huge, they're considerably smaller than the number of subgroups. Okay. And basically what I just said is described in detail in the rest of this section. All right. Now, let's suppose that we really like the idea of symmetric variable pairs, and we want to be able to look for symmetric variable pairs of the 6 different kinds that we've talked about earlier. We can generate a set of Boolean orbits for each one of these. We have comparing F01 to F10, ordinary symmetry, multi-phase symmetry, the 4 types of single variable symmetry. And that's from figure 25. Figure 26 gives the Boolean orbits of each of these comparisons, or each of these relations, assuming that the relation is true. Okay, these Boolean orbits would be able to detect those symmetric variable pairs. So if you want to use the universal symmetry detection algorithm just to detect symmetric variable pairs, it can be used for that as well by using the Boolean orbits illustrated in figure 26. This, of course, is for functions of 4 inputs, for functions of 5 or 6 inputs. It's just a natural extension of what you're seeing here. Multi-phase symmetry. All right, well, should be of no surprise that if we can handle all of the symmetric variable pairs, that we can also handle multi-phase symmetry. It's simply a special case of the previous table. All right. Can also detect complex multi-phase symmetry. That's if we have 2 variables that are inverted with respect to the other 2. We can detect that situation. And the illustration I have here is x1, x2 prime plus x3, x4 prime. That you'd have 2 variables that are inverted with respect to the other 2. And the multi-phase symmetry in this case is it with 2 variables rather than just 1. And we can detect that just as easily. All right. Anti-symmetry. Well, that's, we looked at one way to express that. We take the XOR of 2 cofactors. If it's equal to the 0 function, then they're equal. If it's equal to the 1 function, we say that we have an anti-symmetry. Now, the analysis that I go through in this section shows that in order to detect anti-symmetry, any of these anti-symmetries, what we need to do is we need to use the same Boolean orbits we would use to detect the regular pairs, the regular symmetric variable pairs. Except in this case, we're going to insist, instead of having every Boolean orbit imply either the function or its complement, we want to make sure that no Boolean orbit implies either the function or its complement. If that's the case, then I have an anti-symmetry. And that's one of the reasons that I consider anti-symmetry to be the best term for this sort of thing, because just like when we're talking about anti-symmetry in relations, where you have symmetric relations, anti-symmetric relations, and so on, what we're talking about here is the total absence of symmetry, if you will. And so this is the way to detect anti-symmetry, is we simply change the rules and say, well, in this case, we're making sure that no Boolean orbit implies either F or F bar. Okay, so, and there are 6 types, and we can detect all of them just by changing that rule. Kronecker symmetry. Again, not altogether certain what it's good for. I can say the same for a lot of this stuff, by the way. It's not, I shouldn't pick on just this one. A lot of it is a solution waiting for a problem, and I'm not really joking when I say that. This knowledge is money in the bank, and we may need to cash that check sooner or later, and so it's good to know this stuff. All right, and so we're talking about Kronecker symmetries, the 5 different ones. There are Boolean orbits for them. Here's an example of them for 4 input functions, for 2 of them at any rate, 2 of the 5. We can't simply check for implication or non-implication. What we have to do is this. What we have to do is go through and what we're going to do for each orbit O sub I, we're going to count the number of input vectors that are mapped to 1 by D sub I. And we can test this with respect to this. We're doing this with respect to a function where we want to determine the whether or not a function has a Kronecker symmetry. If the result is an even number, that is, even number of input vectors are mapped to 1 by this function D sub I, which is f ANDed with the characteristic function of the orbit. If the result is even, then it has a positive Kronecker symmetry. If the result is odd, then it has a negative Kronecker symmetry in those variables. All right. And now we come, of course, to matrix-based symmetry, which is my symmetry. Okay. Yes, we can characterize most types of symmetry in terms of matrices rather than permutations. All right, and okay. And so one of the things that's intriguing about matrix-based symmetry is that the matrix groups are so much larger than the permutation groups. And it gives us the possibility of finding many, many more types of symmetry, as we've seen already. And here is, in figure 33, is an example or a list of the number of permutations for n going from 2 through 8, and the number of matrices for n going from 2 through 8. And it starts off relatively modest size, but grows to a very prodigious size very quickly. And so the fact that we have so many more matrices than we do permutations is really an intriguing idea, especially when you get into the larger numbers. Well, of course, for any matrix group, we can compute the Boolean orbits of it. Here's an example of matrix group and its Boolean orbits. This is not the standard representation, obviously. But no matter what the matrix group is, we can find a set of Boolean orbits for n. Okay, and we can build a library of that, assuming that we can enumerate all the groups. We can detect any matrix symmetry by computing the Boolean orbits. Okay. Now, there's a couple of different ways that this can be approached. We can have a library that is computed once, and then we access that. I've actually created libraries for all subgroups of S sub n up through S sub 8. As you may imagine, it takes a relatively long time to do this. I think S sub 8 required about a month of computation time. The others were much faster. It gets real slow real fast. So anyway, we have libraries for any subgroup of any symmetric group up through S sub 8. That's one approach. Another approach is to say, well, we're going to generate the Boolean orbits when we need them. All right? And so I've created a number of generators that can generate the Boolean orbits for particular types of symmetry. We have dynamic generators for rotational and dihedral symmetry. Those are the big ones. And they're also relatively easy to create. We could, using the algorithms described already, do dynamic generation for partial symmetries, but I preferred instead to generate libraries for those because it's not particularly demanding to do that. And so we have libraries for partial symmetry up through 8 inputs. Okay. And we have rotational dihedral symmetry. Another thing that I mentioned when we were talking about various types of symmetry is autosymmetry. In autosymmetry, we have an n-input Boolean function that once we do a linear transformation of the inputs, we end up with fewer than n inputs, or fewer than n linear combinations, if you will. Excuse me. The way an autosymmetric function works is there will be a singular matrix. That is, a matrix that's not one-to-one, that defines that symmetry. And what we will do is we will find the kernel of the transformation defined by that singular matrix. And what that means, it's all vectors that get mapped onto the vector 0. Now, an autosymmetric function, assuming that I've got the right matrix, of course, an autosymmetric function has to map everything in the kernel to the same value. Therefore, the kernel, if I create a characteristic function for the kernel, that characteristic function must imply either f or f bar. All right? And it's also true that the cosets of the kernel all have to be mapped to the same value. Each coset, the elements of each coset all have to be mapped to the same value. The way I get a coset is I take the kernel, add an arbitrary vector to it. Now, sometimes I'll get the same thing back, sometimes I won't, and sometimes I'll get several duplicates. But eventually, if I do this for every element, for every n input vector, I'll end up with the kernel and its cosets. I turn these into characteristic functions, and if the characteristic functions all imply either f or f bar, then the function has that autosymmetry. Now, it's important to note that when we're detecting symmetries with respect to permutations or permutation matrices, that the orbits don't necessarily contain every vector in the vector space. With autosymmetry, every vector in the vector space must appear in at least one coset, and so I will end up with Boolean orbits that include every single vector in the vector space. And so that takes us down to experimental data. I'm going to let you go through that yourself. It describes the sort of symmetries we found. First, looking at all 2 input functions, all 3 input functions, all 4 input functions, and all 5 input functions. Then we went through the ISCAS 85 benchmarks, listed the various different things we found, and then there's 2 other benchmarks that are gate level benchmarks. They're used primarily for logic synthesis, which means logic simplification, fundamentally. And so we went through those, and there are various different types of symmetry here. Okay. I've used the term lockstep in table 42, or figure 42. What that means is that the permutations that define the symmetry have to be applied simultaneously. So I have a 3-3 lockstep. I can't apply these permutations arbitrarily. When I apply permutation to one set of 3 inputs, I have to apply the same permutation to the other set of 3 inputs. And that's what I mean by lockstep. And so there are some interesting lockstep symmetries here. Wreath product, again, that's a hierarchical symmetry. And all sorts of interesting stuff in that set of benchmarks. And here is the number of seconds to detect all symmetries in 1 million functions, obviously generated at random. It's very, very fast. Of course, I stopped at 7 because when we go to 8, it slows down considerably. We have conventional symmetry. Notice that in the universal symmetry detection algorithm, it's considerably slower than conventional symmetry detection once you go to 7 inputs. For 6, the universal symmetry detector is much faster. The reason for the jump there is the fact that we had to express our truth tables in 2 words instead of 1. And that doubled the amount of computation and so slowed things down there. And if you're interested in more information, go ahead and look at the references here. Most of them are fairly interesting, actually. So that's all for universal symmetry detection.